Welcome to the High Voltage AI podcast.
Great to be here.
So this is part of our week-long series in the High Voltage AI newsletter on Substack. We've been covering a lot, educating electric utility engineers on everything from overhead and underground construction to, well, the fundamentals of our grid.
That's right, a really broad look.
And today, being Wednesday, we're tackling something really transformative. Our focus is engineering the future, overcoming virtual power plant integration challenges.
Yeah, this is a big one. We're shifting focus from the broader context to a phenomenon that's really forcing us to rethink fundamentally how the grid operates.
Right, because for, almost a century, distribution systems were designed as these predictable one-way streets, power flowing nicely from the substation outwards.
Exactly, that radial unidirectional design. It's been the core assumption for pretty much every piece of gear on the low and medium kilovolt network.
But that model is getting, completely turned on its head now, isn't it? With all these distributed energy resources popping up, solar panels, batteries, and homes, businesses.
All orchestrated by virtual power plants, or VPPs.
Yes, and they're shattering that whole one-way street idea. Suddenly you've got thousands of generation points pushing power back onto the grid.
It's not just one way anymore. It's becoming this complex, multi-lane, bidirectional highway.
And the existing traffic controls the protection gear, the voltage regulation equipment. They just weren't built for that kind of two-way flow.
Nope. Built for a totally different era, a simpler time, you could say.
So here's the twist, though. If these uncoordinated resources create potential chaos, the VPP itself is actually the key to managing it.
Absolutely. It's kind of ironic, isn't it? A VPP, with its central brain, its control system, takes this potentially messy collection of resources
and turns it into something useful.
Exactly.
Yeah.
Predictable, dispatchable, and actually really valuable for the grid. From a potential liability to a real asset.
Okay, so our mission today is to really dig into the technical hurdles distribution engineers are facing with integrating these VPPs at scale, and critically, how we're starting to solve them.
Sounds good. Let's dive in.
Where do we start? What's the most immediate headache?
Well, I'd say the most common, right off the bat, is voltage regulation, keeping the power quality right. We sometimes call it taming the overvoltage beast.
Overvoltage beast, okay.
Yeah. Picture this. Sunny day, not much load on the system, maybe midday. But you've got tons of solar panels on one feeder, all cranking out power at full tilt.
Right.
All that power getting injected can push the voltage levels way up, especially out towards the end of the line. Far from the substation, goes above the acceptable limits.
And that's not just a number on a meter, right? That overvoltage causes real issues.
Oh, absolutely. First, it violates American National Standards Institute standards, the rules for power quality. Second, it can actually damage customer equipment, think sensitive electronics, appliances.
Wow.
And third, the irony is, it can force the solar inverters themselves to trip offline to protect themselves. So the VPP actually loses the generation capacity it was counting on. It's a self-defeating cycle if you don't manage it.
Okay, so that sounds like exactly the kind of problem a VPP, with its smarts, should be able to handle. How do they do it?
They're perfectly positioned, really. Modern smart inverters, the ones that meet the Institute of Electrical and Electronics Engineers 1547-2018 standard.
Yeah.
That's the key standard here.
The rule book for grid-friendly behavior.
Pretty much. These inverters have advanced capabilities, specifically volt VAR control. So the VPP's central control platform can send out commands.
Commands to do what exactly?
It can tell the inverters to absorb reactive power VARs to pull high voltage down. Or if the voltage is sagging, it can tell them to inject reactive power to prop it up. It's active, real-time management of the feeder's voltage.
Reactive power, okay. And what if the VPP has batteries connected to it? Does that give it even more control?
Oh, definitely. That's another powerful tool. If batteries are part of the VPP mix, the control system can tell them to absorb real power, actual megawatts, during those times of overgeneration.
So they start charging.
Exactly. They soak up that excess real power, which directly tackles the root cause of the high voltage.
Yeah.
It's not just managing the symptoms.
That seems way more sophisticated than the old gear.
It really is. Contrast that with the legacy stuff, substation load, tap changers, pole-top capacitor banks. They were designed for slow, predictable changes in load, not these rapid two-way swings from solar and batteries. They just can't react fast enough.
Makes sense. Okay, so voltage is a big one. But you mentioned protection systems earlier. That sounds even more fundamental, almost like the grid safety net. You said that's maybe the most critical area?
I think many distribution engineers would agree, yeah. Protection coordination, making sure fuses blow, reclosers operate, and relays trip in the right sequence during a fault that's sacred. It's all based on predictable fault current levels and directions.
And inverter-based resources mess with that predictability.
Fundamentally, they change the fault characteristics completely, and this creates new ways the protection system can fail, ways we didn't really have to worry about before.
Yeah.
Engineers are really having to rethink decades-old safety assumptions.
Okay, walk us through some of those failure roads. What can go wrong?
All right, first one, blinding of protection. Normally a fault happens, say, down the line. It draws a huge current from the substation way back up the line. A relay sees that big current and trips. Simple enough.
Got it.
But now, put a distributed energy resource, like a big solar farm, between the substation and the fault. When the fault happens, that resource also feeds current into the fault.
Okay, so current is coming from two directions now.
Right, and the current flowing from the substation to the fault might actually be less than it would be without the distributed energy resource there helping out.
So the substation relay might not see enough current to trip.
Exactly. The current could fall below its pickup setting. The relay is effectively blinded. It doesn't see the fault, doesn't operate, and leaves that fault energized. That's a massive safety hazard, especially for crews working on the lines.
Wow. Okay, that's serious. What else?
Another big one is false tripping, sometimes called sympathetic tripping. Imagine a fault happens on feeder A. That fault causes the voltage to dip momentarily, not just on feeder A, but maybe across a wider area, including neighboring feeder B.
Okay, a voltage sag.
Right. Now, the distributed energy resources on feeder B, which is perfectly healthy, remember that voltage sag, modern inverters are designed to try and support the grid during disturbances, so they inject a large current.
Trying to help, essentially.
Trying to help, yes. But that large current flows backwards from the resources on healthy feeder B towards the substation. And that reverse flow can be high enough to trip the protection on feeder B itself.
So you get an outage on a perfectly good feeder just because its neighbor had a problem.
Precisely. An unnecessary outage caused by the resources trying to do their job, but tripping the wrong protection.
Man, this is complicated. And you mentioned one more, unintentional islanding. That sounds bad just from the name.
It is. It's probably the biggest safety nightmare. This happens when a section of the grid gets disconnected from the main utility supply. Maybe a breaker opens upstream, but the distributed energy resources within that disconnected section keep it powered up.
So the lights stay on for customers in that small area, but it's cut off from the main grid.
Exactly.
Right.
But the huge danger is for line workers. They follow procedures, they open switches, they expect that line section to be dead, de-energized. But it's not. It's live because of the local generation. Extremely hazardous.
So how do VPPs prevent that? They have to, right?
They absolutely must. Robust anti-islanding detection is non-negotiable. The VPP control system has to detect that loss of the main grid connection instantly and command all the resources it controls to stop generating, to cease dispatch immediately. This isn't just a good idea. It's a core safety requirement baked into that Institute of Electronics Engineers 1547 standard. Worker safety depends on it.
Okay, it's clear the software, that the VPP control system is doing some heavy lifting here, but it sounds like software alone isn't enough. We can't just, code our way out of these physics problems entirely. We need hardware upgrades too. Physical grid modernization.
You absolutely do. Sophisticated software is the brain, but you still need the brawn. Integrating VPPs at scale, especially high concentrations of them, often means real physical upgrades to the grid itself.
Like what kind of things?
It could be anything from replacing older, smaller wires reconductoring, because the lines now have to carry power in both directions, sometimes significant revert power flow. Upgrading the service transformers that feed homes or businesses.
Right.
And definitely upgrading protection devices. Installing newer microprocessor-based relays that are smart enough to detect power flow and fault currents going in either direction, not just one way.
And managing all this increased complexity, the two-way flows, the VPP actions. Utilities need better visibility, right? Better control rooms.
Far better visibility and control. This is really pushing the adoption of what are called advanced distribution management systems, or ADMS.
ADMS, not just the older SCADA systems.
ADMS is often seen as the next evolution, integrating more real-time data, more modeling. Think of it like the grid's air traffic control tower. It pulls in data from smart meters, sensors out on the feeders, integrates it with sophisticated power flow models.
To give operators a complete picture.
A comprehensive real-time view. This lets them manage VPP dispatch requests alongside the operation of traditional equipment, the capacitor banks, the regulators, making sure everything plays together nicely. It's about orchestrating the old and the new.
And underlying all of this, you keep coming back to standards.
Because they're foundational. Especially Institute of Electrical and Electronics Engineers, 1547, 2018. That's what mandates the smart inverter functions, the capabilities like volt-VAR control and anti-islanding that allow these resources to be, good grid citizens instead of just sources of problems. And organizations like EPRI, the Electric Power Research Institute, they provide a ton of research and guidance to help utilities figure out what upgrades are needed and how to change their operating practices.
This sounds like it impacts not just operations, but how utilities even plan the grid for the future. The old planning methods must be completely out the window.
It's a profound shift, a complete paradigm change in distribution planning. The traditional way was basically make sure the system can handle the single hottest hour on the hottest summer day, the annual peak load, designed for that one worst-case snapshot in time.
That's it.
Largely, yes. Make sure the wires don't melt and the voltage stays okay at that peak. That approach is, frankly, obsolete now.
So what's the new reality for planners?
The new reality is they need to analyze how the grid behaves, not just for 1 hour, but for thousands of hours across the year, under countless different scenarios of solar generation, battery charging and discharging, changing loads. It's incredibly dynamic.
Wow, that sounds like a massive increase in just the sheer amount of calculation needed.
Monumental increase in analytical complexity is exactly right.
Yeah.
You can't just run a simple peak load flow anymore.
So what tools do they use? It's not the back of the envelope anymore.
Definitely not. It requires sophisticated simulation engines, software that can run time series analysis over thousands of hours. And it needs massive amounts of data, really granular data about generation profiles, load profiles, maybe even down to the individual meter level.
So forecasting becomes way more important. Predicting solar output, battery use.
Hugely important. Accurate forecasting of distributed energy resource adoption, how people will use their batteries, combined with detailed load modeling. That becomes the core skill set. The planner's main tool shifts from a simple power flow program to these complex forecasting and simulation platforms. It's a totally different job.
Okay, we've covered voltage, protection, physical upgrades, planning. Is there one ultimate bottleneck, one final barrier we need to discuss?
I think there is, and it might be the trickiest one: communication and data interoperability.
Interoperability, making different things talk to each other.
Exactly. Think about it. A VPP isn't one thing. It's a system of systems. You've got the VPP platform itself, utility control systems, thousands or hundreds of thousands of devices out in the field, inverters, batteries, smart thermostats, often from dozens of different manufacturers.
Right. Everyone uses different brands.
And getting all those different devices made by different companies using different protocols to communicate reliably, securely, and with very low delay. That is a formidable obstacle. A VPP is only as effective as its weakest communication link.
It sounds less like a traditional power engineering problem and more like an IT integration nightmare on a massive scale.
That's a good way to put it. While the challenges with voltage or protection are, fundamentally understood electrical engineering problems, we know the physics, we have technical solutions, even if they're complex or expensive. This interoperability issue, getting everything to speak the same digital language, that falls more into the realm of standards, bodies, communication protocols, cybersecurity experts. It's less about electrons and more about bits and bytes and agreements.
So solving that communication and standards piece is really the key to unlocking VPPs everywhere.
In my view, yes. That interoperability challenge is the critical path. Solving it is what will truly allow us to scale VPPs up and realize their full potential across the entire grid. It's the glue that holds the whole concept together at scale.
Wow, okay. So summing this up, what we've really unpacked today is that integrating VPPs isn't just about adding some new software. It's forcing a fundamental re-engineering of the distribution system top to bottom, from the physics of how power flows to the way we plan and operate it.
It really is a fundamental rethink, challenging almost everything we took for granted about the distribution grid.
It makes you wonder then, as these grid modernization efforts keep going and the lines blur between traditional utility hardware and this sophisticated software control, how does the job of the distribution engineer change even more? What skills become absolutely critical in the years ahead?
That's the million-dollar question, isn't it? Something for everyone in the industry to think about.
Definitely food for thought. Well, this has been incredibly insightful.
Glad we could cover it.
And for our listeners, if you'd like to leave feedback or have any questions about today's deep dive, please feel free to reach out to our producer, Julius Guay, that's Guay, pronounced Guay on LinkedIn. We always appreciate hearing from you.